Adventure, the human rocket. The purpose of this lab was to analyze and model the motion of a man free falling from the sky, trying to break the sound barrier, test the speed of sound model for air, and figure out an appropriate model for drag. Using Newton's second law equations, we could accurately predict and update the man's velocity and position. To use these equations, we had to calculate the net force on the man with the effect of air resistance. The goal of the modeling was to see if he could actually break the sound barrier. To do this, we can analyze his velocity. After analyzing the data, I could conclude that we were able to accurately predict if he could break the sound barrier. Using Newton's second law equations to the right, I am able to calculate the updated position and velocity of an object at different time intervals. These kinematics equations are very useful in modeling an object's motion and are derived from the momentum principle, which is mass times velocity. These kinematics equations also involve net force. For this experiment, the net force includes both gravity and air resistance. Since resistance has a big impact on free-falling objects, we have to account for it in this experiment. This means the net force would be the force of gravity plus the force of drag. Drag acts in the opposite direction of the motion of the object as the diagram above shows. In many scenarios, we don't account for the effect of drag, but that does not mean it is always negligible. We can predict that a model that accounts for drag will be more accurate than one that does not, since it is closer to the true net force in the real world. When an object is in free fall, it could reach its terminal velocity, which is the max possible velocity it can go. This is the equation for the terminal velocity, which accounts for air density, the drag constant, V or C, and when an object reaches terminal velocity, its net force is zero, since the drag force will be equal to the force of gravity. For this experiment, the system is Felix Baumgartner, and the surroundings are everything else, such as the Earth and the balloon he jumped from. The initial conditions for this lab are that Felix starts at his initial velocity, 0 meters per second, and his position starts at 36,500 meters above ground, since he jumps from 1,000 or 120,000 feet above ground. The drag constant B I found to make his fall accurate was 0.000001. For this experiment, I used one of the provided videos of the human rocket. I analyzed Felix Baumgartner's record-breaking jump and compared his free fall to the principles of physics we learned about. I used the length of his free fall, which is about 4 minutes, the typical density of air, and average mass of a male, and given starting height to do my calculations. I would predict that as Felix falls, the magnitude of his velocity would keep getting bigger and bigger, and that he would break the sound barrier. But if he reaches his terminal velocity, then his velocity would stop increasing. To break the sound barrier, he would have to go greater than 343 meters per second. Through coding, I was able to model Felix's fall according to the principles of physics that we learned about. I used assumed values about air density, weight, and the given height to make any calculating accurate. I used the drag force formula to account for air resistance in the model and found that the constant B should be 0.000001. This is why my calculation for F net includes the force of gravity and air resistance. I used a loop to calculate the predicted position and velocity at each time interval using kinematics equations since force is not constant. I used the terminal velocity equation to check if the man ever reached that velocity, since physics principles state that you can't go faster than that, and coded his velocity to stop increasing and for f net to equal zero. Here's the output of the prediction model for during the man's fall. It shows the start and the stop. From the analyzed video, I know that Felix did break the sound barrier, and the data showed that he reached 377.12 meters per second, which is greater than the required speed to break the sound barrier. And the data from the model shows that the magnitude of it is increasing over the time. Through this experiment, I can see that in the predicted model that Felix would reach speeds greater than 343 meters per second, which is the speed necessary to break the sound barrier. This is based on the magnitude of the y-axis of the velocity time graph on the last slide. This lines up with the observed data that says Felix reached a max speed of about 377.12 meters per second, which is also greater than 343 meters per second. This means my predictions were right and he did break the sound barrier, and that you can use kinematic equations associated with net force and velocity to calculate changes in motion. I found that the constant B would make an appropriate model for air resistance was 0.000001. In conclusion, it is possible for a human to break the sound barrier if you are dropped from a high enough point. A source of error could be human error when making the calculations. Another source of error could be in the assumptions I made for the predicted model. They would cause differences from the observed data and the actual motion of the fall. I did not account for when Felix released his parachute, which would have slowed his descent. For the what if, what does it mean questions. Terminal velocity happens when a freely falling object experiences zero net force. Did Felix reach a terminal velocity, and what does this mean for Felix trying to reach the speeds necessary to break the sound barrier? Yes, due to how high Felix jumped from and how fast he was falling, he eventually reached a terminal velocity, and he was traveling at very dangerous speeds. This means that Felix had to jump from a high enough point so his terminal velocity would be higher than the speed necessary to break the sound barrier. What is the effect of air density on a falling object, and what does this mean for Felix's fall, and how was he affected by it? The density of air increases as you get closer and closer to the surface of the Earth. This means that as Felix was falling, the density of the air around him was changing, and this would have an impact on him. As density increases, his velocity would be a little smaller, but he was moving so fast that this is hard to see in the actual data. His terminal velocity would also be lower since density is a big part of the calculation of terminal velocity.